is not discrete. The world is continuous. And so we have the world and we have our computer, right? I'm not even going to draw a box around the world. It's like just everything outside of the computer is the world, right? So everything inside the computer box is discrete, and everything outside is continuous. So there's no way to do continuous calculations in the computer. I mean, actual manipulation of signals inside the computer will always happen on a discrete level. Now, how do we get from the world into the computer? By means of a sample. Okay, and how do we get from the computer outside? We need to do some kind of reconstruction. And as I've mentioned before, the simplest version of a reconstruction device, the one with the lowest latency, is a zero-order hold. And so inside the computer, we now have discrete calculations. And so from the point of view of an algorithm, if we're trying to describe an algorithm, that operates on a discrete signal, we will write that algorithm as a discrete transfer function within the mathematics that we're doing. And we will then, in order to make that something that operates in the real world, the thing that comes out of this zero-order hold will be this classic stair-step kind of function where we are reconstructing by simply taking the last value, or we're taking that value that the discrete system outputted, and we're holding it. So zero-order holds are very easy to implement. Easy ways of implementing zero-order holds include something like just kind of a billboard. So you can imagine having a billboard with like digits. Everything where you just write something down when you get that new value and you update it when you get a new value is effectively a zero-order hold. Because the value, if I look in the intervening time again at that board, what I will see is the last value that you wrote down. And so kind of, it's the obvious thing. And when we're using something like Python code, a zero-order hold is effectively the automatic behavior of variables. So I update a variable at a certain moment in time, and if I look again at that variable in some intervening time, it will just have the value that it had last time. So zero-order holds are easy to implement, they have very low latency, and they are the kinds of things that we will be studying in this course. And so at this point, right now, is the first time that we're going to do math where we are actually making errors, where we know that we are making errors, and that we are trying to think about how big those errors are and how those output signal will differ from the original signal. So does everybody understand that I'm making an error in this reconstruction? So even if my computer were trying to do nothing, let's say GZ is 1. What does that mean? It means the output okay, this is the difference equation that describes the do nothing operator. It would follow that y of t was equal to u of t if that were a continuous transfer function, right? But it's very clear to see that if this is u of t and this is y of t, with my computer system, I am unable to build a system that is transparent. In other words, I'm unable to build a system that has the property. Hello?
So I must just come and check if you've connected your network cable in there.
No.
Not.
Seems to be working fine.
Yeah, but we can't pick it up on the system.
Okay, I'm sorry. But yeah, I haven't connected anything else. So because I have issues with reconstruction, I am now unable to build a transparent digital device. And so here we have the first problem with sampled signals, is that because there's always this reconstruction process, I am unable to build a transparent digital device that is transparent both in function value and in time. So as I mentioned before, if I do all the things that we spoke about, if this signal is band limited and I sample at a sufficient rate, according to the Shannon-Nyquist theory, it is possible for me to reconstruct a signal offline. In other words, it is possible to get back and know what U of t used to be. It is not possible to build a device that operates like a continuous transfer function with the value 1. Because a reconstruction will always introduce at least some time lag. And so when we implement digital devices that operate similarly to analog devices, we are always bound to make some approximation error. And this is one big important thing for you to remember, that we can never find an exact equivalent of a continuous system in the discrete domain. This is fundamentally impossible. Now what that means is if you look at this box, imagine that you already had an analog version of some kind of filter or a controller or some system that did something interesting. Maybe it's a filter, right? Maybe it's like trying to remove noise. And a vendor approaches you and says, "Oh, shame, man, I see you're still on that old analog technology. I have a computer here that does exactly the same thing as this analog technology." Right? So I will replace your analog box with a digital one, and it will work exactly the same. We know from this basic idea that it cannot work exactly the same. At best, it can promise to approximate the original analog system to some degree of accuracy, especially when we're thinking about implementing that in real time. And it's important to just make that distinction. A digital box can completely reproduce an analog signal flow as long as we allow for some latency, as long as we allow it time to do its thing, right? But the output, the reconstructed output, will always be delayed if we're actually working real time. And you can refer back to our filter discussion to kind of understand why that would happen. So the more of the signal I'm using to do the reconstruction, the longer I have to wait for just like to actually receive those samples, which means that I cannot report those answers faster than at least that window of signals that I'm using. Okay, and because of that, there's always a delay. So once we start talking about reconstruction, and definitely once we start talking about reconstruction within the context of control where low latency is very important. Why? Because I'm wanting to act on the reconstructed signal. I want the reconstructed signal to operate things in the world. I want it to move valves or to open up the electricity flow or whatever. And every time that happens, it's going to be a little bit later if I'm using digital control than if I were using analog control. And so at best, we can say that there are many other advantages to using digital devices, and maybe it's worth it, and maybe we can get an approximation that is sufficiently close to get there. And so let's just talk about a couple of different applications or places where we think about approximating analog systems using digital systems. And I want to, I know that this is it's hard. I've spent a lot of time trying to imagine the different ways in which we talk about the Z transform. And I want to have these kind of pictures here so that you understand what we're trying to achieve. So the picture that I have here, where I've got the world interfacing with the computer, interfacing again with the world. This problem you can call as, you can say something like a digital equivalent. And there's a problem where you can say, so the problem basically looks like, if I used to have g of s in that exact same position, what should g of z be in order to get a good approximation of the relationship between u of t and y of t? Is that making sense? So this is like the answer to, this is like if we're kind of analyzing problem types, right? This is one problem type where we are doing the Z transform on a continuous, like in a problem statement where there is a continuous transfer function. Is this making sense? So you've seen, let's say, problem types. Let me just summarize the problem types that we have already, right? Find the Z transform of a signal. Right? We know how to do that. Okay, and you can imagine that as saying, well, if that's the kind of problem statement, the problem statement will have the continuous version of a signal of time. And I could specify that two ways, right? Because we know that there are two ways of specifying this, or let's say 3 ways. So I can give you f of t, I can give you f of s, or I can give you effectively a sampled version of f of t in the form of like a spreadsheet, right? And so you know if that's the problem is like, here's a function, find the Z transform of the sampled version of that signal, right? Here's a Laplace transform of a signal, find the sampled version of that signal. Here is a table in Excel, find the Z transform of that. Okay, and various perturbations of that. I could draw the function instead of giving you the function of time or any of that kind of stuff, right? The second problem that we've already done is find the Z transform of a discrete system. Okay, and discrete systems, remember, are specified using discrete difference equations. Also, other kinds of ways in which I can specify this, something like a 10 element moving average is also a discrete system. And you can actually write down a difference equation for that. Right? All the discrete filters that are in the textbook are discrete systems. And they have, as their describing thing, a discrete description. Okay? So I'm thinking about just like problem statements, right? Problem statements, when you look at it and you're like, okay, I know I'm supposed to end up with a Z transform. In the problem statement, they give me one of these things. If they give you a continuous function of time or a sampled signal or a system that is already in terms of difference equations, you already know how to do these problems. Okay, that's what we've been talking about this whole week. I'm introducing now a third problem, which is find the Z transform, or actually just say find g of z given g of s. Now that's what the problem, like those are the main, let's say, defining characteristics of that problem. But you have to understand that that is a fundamentally different kind of problem. Okay, because the first two have clearly defined singly correct answers. Or let's say there may be multiple answers, but they all are identical in mathematical terms. Right? And there's only like, let's say, I can easily say that this is the correct one because the error is 0. As soon as we say, I give you g of s, if that's what I start with, here's one version of events, which is if I have currently an analog system and I would like to build a digital approximation of that system, given g of s, find a value of g of z, which will make that approximation okay. Now there's a couple of versions of that problem. Now, I'm going to do a slightly easier version of the problem first, which is, what if we have differential equations of time describing that system? Right? So remember that we know an exact form. We know exactly how to handle the case where I have a discrete system, a difference equation, right? So I've got a Z transform. I'm trying to do that on a difference equation. I just need these. And so one kind of obvious route from a continuous system to a Z transform is to approximate that continuous system using discrete difference equations. And the obvious route to do that is to take that derivative and do something like a first order difference approximation to that derivative. So to say something like, well, dx dt is approximately equal to xk minus 1 divided by delta t. And if I do that with all the derivatives, I have now converted my continuous differential equations to discrete difference equations. And I now find myself back there, and now I can continue easily and find that equivalent Z transform. Does that make sense? And so that's one answer to this question. Simply take the continuous description, discretize the continuous description, and then continue as before. Do the Z transform as before, and now we have a G of Z that does approximately the same things to its input as the continuous system would have done to its input. Does that make sense to everybody? Now, what if I actually started with G of S? Well, and you'll see that this is this idea that I've written down here, this finite difference approximation is also called a backward difference approximation. Why? Because we're going one step back in time. So we're taking xk and we're subtracting xk minus 1. Obviously, we could also have used a forward difference approximation. So we could have taken xk plus 1 and subtracted xk. And that would be mathematically equivalent, but it would be non-causal, because if I did that at time k, I wouldn't have access to the events at time k plus 1. If I were doing this real time, I only have access to signals in the past, right? And so this backward difference, when people talk about a backward difference approximation, what they mean, the back and forward there is back in time versus forward in time. And so they're saying, well, if I were looking back at time and I just had all the values that I know so far, what would my estimate of the derivative be? Also take note that this is not a unique solution to this approximation problem. There are higher order derivatives or higher order approximation methods. I can kind of average out the derivative over the last 3 time steps, say, right? And so we can use wider windows to make our approximation, and those will have kind of pros and cons. They'll be longer to calculate. They'll have a greater latency. They tend to be more accurate on smooth signals and so on. So there's a couple of different reconstruction or discretizations that we can do. The only one that I want you to know by heart is the backward difference approximation. But the most important thing that I want you to know about these things is that these are very different things. So in other words, when I have if I have a differential description of my system, that's an exact relationship. As soon as I introduce this backward difference approximation, I am doing an approximation. And while it may sound a little petty, I really love subtracting marks when you tell me that this is an equality instead of an inequality or an approximate. Because you have to understand the difference between, you have to understand when you are introducing errors into your calculations. It's not just me. if you actually take the time to read this textbook section about backward difference approximations, you will see very loudly signposted, like you shouldn't be doing this approximation if you have any alternative. But if you just want like a quick way of doing this, and why this is so attractive is because you can imagine doing a Laplace transform of this and saying, well, if I Laplace transform this thing, I end up, so Laplace transforming that gives me s times x of s, right? If I z transform this according to my rules, right? Let's do that I end up with x of z minus x of z times z to the minus 1 divided by delta t, right? And if I do this, I can kind of tell myself that the transfer function here, so because I can rewrite that and extract x of z, right? And I get 1 minus z to the minus 1 over delta t. And this thing and this thing are in equivalent positions relative to that signal.